Oops. Okay, and everybody, it looks like we just lost. Yes, we just lost Mark. Okay, Mark said his laptop just died. So I think everybody, should we go to open discussion now?
Yeah, we can move to open discussion, I guess, if you guys want.
We'll move to open discussion. Okay, Jeremy, I wasn't sure. Yeah, so let's do that. We'll plant the flag. Open discussion time.
Mark can always come back on if his laptop comes back up.
Yeah. So Jeremy, what do you think? Is mainstream is the safe stream?
Yeah, Simon in the chat said science advances one funeral at a time. I don't think we have to be quite so dark, but mainstream is safe stream. I tend to agree. We're kind of like fringe. This is a topic that's been considered fringe, and but at least as long as we're using acceptable physics and we're not trying to throw out all of the accepted physics, and we're going off academically accepted methods, then I can see why some people might not choose this as a field. But man, like I don't understand why more people aren't into this. Like this is the whole reason I wanted to study physics, because I wanted to learn how to do anti-gravity and understand how gravity works and unify the four forces of nature and stuff.
Jeremy, if I could offer a thought though, and this is, I'm just kind of thinking out loud here, but your channel, you're at like what, 110, 120,000 subscribers, right? And you talk about this stuff all the time. I mean, this is your forte right now. I know it's taking you a long time to build that up, but let's say 110 conservative, 110,000 subscribers. This conference, this interstellar conference, maybe, I don't know, a couple hundred at the most, a couple thousand on a wonderful day. So in a strange sort of way, you are the mainstream. You're reaching the mainstream, and so it is kind of strange in a sense.
If only the numbers were bigger, man. I got a lot of my subscribers early on with YouTube, because I've just been around for so long. My channel, I started in I think 2008. So that's part of the reason I have so many. A lot of them are probably inactive accounts and stuff. And but we do reach a big audience. I mean, considering that it is a technical subject matter, and you've reached 3,000 people on a stream like this with that you're getting at least some of those people are technical people who can understand this on that level. I found that whether or not the community is on this level and ready for this yet, like a lot of people have commented that the stuff that we talk about on these discussions is way above the pay grade of UFO Twitter or some of these other communities and stuff. But it is that are there, those people are more on the fringe, I'd say. So it's all right, because they're catching up, and it gives them something to work toward, and also gives younger people something to like, oh, there's a whole bunch of curriculum that I can study now. This is there's actual papers that I can read, and scientists that I can talk to and get advisement from on my direction in school and stuff. So I've learned a lot from watching the speakers who've come here, like figuring out which colleges you should be going to for what. And if you want to get involved in this type of research and this type of stuff professionally, I think that's super important for the next generation that's actually going to build these craft. I look at my kids are still young. When they grow up, are they going to how are we going to get there in a generation? When my kids are graduating high school, how are we going to get from right now to 18, 20 years from now, when they're going to college and starting this stuff?
Well, and they'll be bored with rockets by then too, right? I mean, Elon Musk today, that's kind of exciting, but by the time they're going to college, they'll be like, well, that'll be the same way we look at Apollo. They'll be like, okay, that's it. What have you done since then? So yeah. So it's interesting. There are a lot of other things too. I mean, I think that the mainstream is moving forward, and so stuff like modifying gravity doesn't seem as silly anymore. I mean, you look at like quantum computing, right? I just saw a new story on quantum supremacy like yesterday. They just hit a brand new level. They did in 4.5 hours what a regular computer, like a supercomputer, would take thousands of years to do. You know, and that's real world, right? And that's advanced quantum mechanics. So if stuff like that is already being done in the lab, then how far away is stuff like, you know, warp drives or gravity modification, things like that?
Right. We're approaching this singularity, I would call it, with in terms of the technology, with the material science is now reaching that level where we can, you know, lock on and manipulate the very fabric of space time. And I don't know. I think it's part of part of this is, you know, people have talked about disclosure and that there might be people in the government that don't want this stuff to come out. Well, there's lots of people in the government that do want this stuff to come out, and but also safe, albeit safely. And I think that we're doing that a responsible job of, you know, making the scientific community feel the presence of this technology that is coming out, and to prepare humanity. The next step is to prepare like humanity for, you know, the step that's going to take, because we're not, if we have the technology to do warp drives, you know, we need to find ways to use that, not in way, you know, in safe ways, to constructive ways to help save humanity, because this technology is going to empower us to save our species and have absolute freedom, or it could, you know, be absolute enslavement if someone like Kim Jong-un got a hold of this technology. So it's certainly a discussion worth having, but again, and the material science is the key part of this, because it's not like even the theoretical stuff that we talk about here is hard for someone like Kim Jong-un even to physically obtain, because he'd have to go through the logistics, and it's going to take a cooperative community effort to build this technology. And I think that's an important part of this, because if it were a low-hanging fruit and it were too easy to replicate or produce, then and anyone could have it, and that would be quite dangerous. And I think in order to achieve this on a global scale, we're going to have to come together globally, and that's why I like the fact that this is an international conference, and it's open to, you know, anyone in the world as long as they speak English.
And if they bring a translator, we'll do other languages too.
Yes, that could happen in the future.
Yeah.
Sure.
Well, and I like the fact that our conference is kind of mellow, you know. I think that makes it work.
Mellow is key.
Oh, you're back.
Yeah, I'm back. The computer died literally as I was plugging it in. So it was perfect timing on that end. We are going to have more of the poster presenters coming back. So hopefully in the next half hour or so, I'll charge up my laptop a little bit here. We'll be able to go back out there and grab the last few of them. I see Mark Preston, who was one of our interviews, is now joining the conference.
Yeah. So and Mark, I was going to say we're in open discussion now, just so you know. So, and you know, I think things are pretty quiet. And yeah, I like the mellow thing, and I think the fact that you're basically reporting on another conference is truly a breakthrough, you know. And I hope that our audience, like the people watching on YouTube, I hope that they're able to learn more about IRG the same way that they learned about Tesla Tech, right? And
here's something really cool that I wanted to show you. So I actually brought a book on high-powered microwaves to the conference, thinking if I have any spare time, I'll read up on this and try to learn a little bit more about, you know, the Klystron, the setup that I have over there, make sure everything's okay. Turns out the author of this book is one of the presenters. So I went to talk to him, got him to sign it. He doesn't believe in UFOs too. He thinks that they are a weather phenomenon. So I gave him a copy of David Alzafon's book, Gravity Control with Present Technology, and told him that we're building weather phenomena that will get us to Mars in a couple minutes. And he actually signed the book for me. And
there you go.
Nice.
Yeah. So that is, you know, us pulling the mainstream toward the technology a little bit. And he's now very interested. He's going to read David Alzafon's book and see how it's connected to high power microwaves. And He
I-
never even
tell
heard
him
of EPR before. He never heard of electron paramagnetic resonance, which is strange because that's what you use high power microwaves for. And he actually wrote the book on it.
I see Mr. Boyd laughing on camera.
Here, James Benford, and here is his signature, James Benford. And
Nice.
I got the Polaroid. Had
There
to
you
get
go.
the Polaroid.
There you go, man.
Had to get the Polaroid of him signing it.
You're pushing the balloon.
Yeah,
We're pushing really hard. I'm very pushy.
Tell them to also check out PBS Spacetime's latest video on how matter arises from electron spin. That was a really, really
one
good.
step
It's
at a
like,
time.
no, it's like Alzafon in reverse. He like literally lays out like how spin gives a rise to matter, and it just like if you do it in reverse, it's Alzafon. It's like, oh my god,
Yeah,
it's
yeah,
coming
yeah.
out to the mainstream. Yeah,
Post a link to that, or actually send me a link to that on WhatsApp. That's a video that I really need to watch.
yeah, it was good. It was like 23 minutes long. Let me find it. PBS.
Yeah, the average age here is pretty old too. I'm probably one of the youngest people here.
This is it. It's this one right here. I'll post a link to it right in the live chat.
Why did you make?
We were handing them out.
So now there's that temptation. Now that we know that Mark is willing to travel, there's like, let me see, what conferences could we send Mark to? Just how far can we push this envelope?
Oh yeah, we were handing out little flyers about the conference.
That's awesome. You're organizing. That's what you're
Yeah.
doing.
Yeah, we were
You're
handing these
organizing.
out. People love them.
But you paid for the conference too, right?
Canvassing.
Yeah, I paid for the conference. It includes, dinner, and we met some cool people and scared off Sonny White. And
Although in his defense, right? Yeah, I mean, he has to do fundraising for his lab and his projects and stuff like that. So I would
Yeah, I
imagine
mean-
that he's quite a busy person.
So
not
Mark,
just
today-
that, but what we're doing is really dangerous for him, because if he's not on board and in front of this technology, then he's just going to get run over, and he knows it.
so do they have a bar there?
Oh yeah.
Are most of the people that are there at the bar, or are they like milling around?
No, it's almost 6. Give them about 10 minutes and they'll be there. Yeah, that's how these things work.
They're at the bar. Yeah. Actually went out partying with Glenn Robertson last night.
Yeah.
Oh, yeah, I bet
Yeah.
that was fun.
So Glenn was tagging along with this college reunion people they were all drunk off their ass, and we tagged along with him, and it was just a bunch of fun.
So now, how about the?
Glenn bought me a drink.
Are many women there?
Not many women. No, there aren't many women. And there aren't many women over. I mean, APEC is doing okay comparatively to the scientific community, but we have Noel and Laura on. We have also had what was her name from?
Oh yeah, yeah. And she's wonderful too.
Yeah,
And Brenda.
Well,
yeah, Brenda was the camera woman, but
and then we're hoping to have Chantel Butler on, and then again, Chantel is, and Mark knows more about this than I do, right? So her company, Geometric Space, I think that they actively want to just let people know that they are willing to take payloads up. And so she wanted to come on and talk about that. And what I suggested was, I said, look, if you want to come on, tell us more about what you guys are doing. So she hasn't said no, but she had a conference this
Well,
weekend
I
she had
think
to go
people
to.
are afraid of the stigma.
No, they're afraid of Mark's hair. They're afraid of Mark's hair.
Oh
That's
yeah,
the-
well that could be too. But
I'm
but
just
well,
teasing.
and Mark, didn't you say that most of the people were, say, over 40 that were there?
yeah, I would say most. If
Did you
if
say
most
they're
is-
retired? They're retired.
yeah,
people?
most of them are retired. Yeah, most of the
Yeah,
people here are retired.
so there would be a lot. So as you get to the older crowd, the stigma is greater, wouldn't you think?
Yeah.
Yes, because they're set in their ways.
Well, plus they've
It's
been
that-
beaten down for 20, 30 years. If they even said anything, they'd they'd be in the unemployment line. So it's kind of like the stigma is slowly going away, but you got to keep pushing that balloon.
Every old scientist that passes away is where the stigma goes. Because
Yeah, well, you got to keep pushing the envelope there. That's the thing. I think that's a great idea.
there's some
Going
people
to
that will
the
never change their
conferences.
mind,
And,
but you can change their kid's mind.
what's that? Say it again.
Some people will never change their mind, but you can only hope to change their kid's mind.
Well, you can change their mind if you can show them something. If you can show them some.
Have you heard of
It'll
there was a
take them a
UFO
while to
incident?
accept it.
There was a
take them
UFO
while to
incident on a
accept it.
commercial flight, and it happened for quite a while, and all the passengers were looking out the window and pointing and screaming, whatever. And there was this psychiatrist there that refused to look outside the window, saying he doesn't believe in UFOs. That's a psychiatrist.
Well, maybe he should have been a physicist. He would have been,
Might as well could
he would have been more open.
It would have been more appropriate, right? I'm
Yeah.
gonna.
Oops. Oh, and that was Mark's. Oh, Mark, you're muted. Okay. Oh, yeah, because I think you were getting background noise.
Oh, I said I'm gonna go check out what's happening out there. So I'll be.
Oh, okay. Okay.
Nice.
Yeah, I don't know. Well, it is interesting. I don't know. Michael, I think what you're saying is right. If it's a crowd with older folks, you're more likely to have stigma that, people are more indoctrinated, right? And that kind of things are changing though. We live in a world with 16 genders now. If we can live in a world with 16 genders, then we could talk about warp drives in public.
Well, we already always had the 16 genders. We just now figuring it out. That's all. It's like the culture is lagging behind the technology. There's a hysteresis that we're dealing with. But if we keep pushing, eventually it'll go over, right? And it's with the government basically coming a little bit out of the closet about what they know. I think that's making it more acceptable. It's more, it's reducing the stigma.
Yeah.
Yeah.
Yeah, no, I think that's true, and again, from a pure science perspective, I think a lot of the ideas that drive these technologies, right? Like Alcubierre and stuff. I mean, Alcubierre is taken for granted. It's not, I would say that most traditional scientists don't consider it feasible, but I think that they look at the physics and say, okay, this is in general how it's done. It's not considered, out there too far. It's like, if you're going to do it, this is how you can do it. We just don't think it's possible. Well, so over time that changes, right? From, it's kind of like fusion research, right? Like, there's no way it can be done, and then maybe we can do it, and then, hey, we're getting a little bit of results, and
So now I'm curious. I had a couple of, is Ron still on? Ron Kita?
Ron is. Let me see. I'll click ask to unmute. And looks like Brenda just joined again. Brenda,
Hello?
if you can hear me.
Yeah, hello?
Oh, there's Ron. Okay, you're not Brenda,
Hey,
but I was going
Ron.
to say
Oh,
thank you to
sorry.
Brenda
Oh,
for the.
I got it. Never mind.
No. Yeah, Michael had asked about you. I was just going to say thank
Yeah,
you
I
to Brenda
sent you.
for taping.
I sent you a chat message about. You sent a video out a couple of days ago about gravity shielding, where you had some experimental results, and I wanted to check with you if it would be okay if I share that.
Yeah, okay. I want to mention, I'm unmuted. In terms of what it is, I've gone beyond those results.
Oh,
The only reason why I published it is because it was going downhill. And with making electrets, there's no guarantee. There's a lot of the chemicals I have to make myself because chemical suppliers do not want to sell me. I got to sell my firstborn son to get a chemical. And so I make the damn things myself. But yeah, if you want to give that, what I did is I put I put it on LinkedIn, and there's another one Did you see the one on unipolar electrets?
I have the one I have is where it shows, basically you have the can with the
Yeah,
electric,
yeah,
and then you
Well,
flip it
well,
over and there's a weight loss. And
Yeah.
that's what I wanted to
yeah.
share.
Okay. What I wanted to say is the only reason why I made that because it was going away. And I said, if I wait 2 more days, I may not get it back for months. And I put it up
Oh.
quickly and I didn't want to share it because the results, but I have since, hold, can you wait? If you wait on it, I can show you something on the screen a second. Who's
Oh,
next?
yeah. If you got something else that you'd like to show that, it'd be fine.
Just wait a few seconds. Just hang on here.
Okay. So, and then there was this other thing I wanted to talk about, to deal with, basically virtual electron pairing. And there was a couple of the speakers were talking about creating antiparticles from photons, stuff like that. And so, but let's wait and see what's up with
Carl said Cooper pairs. Carl,
Cooper. No, it's not Cooper pairs,
No.
but
I'll drag Carl in. He's being quiet.
No, I love the idea of virtual subatomic particles, and it's a great idea. I mean, I just assumed that's what you're talking about because of type 2 superconductors, but that was what I thought you were indicating.
Oh,
so yeah, what I'm talking about is, hold on, can you guys see my screen?
no, you have to finish screen sharing. You started it, but you haven't finished. There we go. Oh, and there's Ron. There's Ron's as big as life there.
Yeah, so here's this thing I wanted to show you. Okay, it's talking about why pair production cannot occur in the vacuum, empty space. And this is like, I've advanced it to the parts where basically he's talking about what the paradox is.
Down to basically conservation laws. So if I look at the conservation laws associated with this process, specifically the conservation of energy and the conservation of momentum, as I'll show you, we cannot conserve energy and momentum simultaneously for this process if
Uh-oh.
Something happened. Oh, it's just locking up. It'll come back.
if there is no external material or an atom or a nucleus present nearby. So let me show you how we can come to that conclusion. So let's look at the conservation laws of energy and momentum for this particular case. So you have a gamma photon, which is extremely high energetic. The energy of this gamma photon is greater than this quantity. Why am I drawing the diagram in this particular manner is that the gamma photon, if it is moving in this direction, has some initial linear momentum in this direction. All right. The gamma photon does not have momentum associated in this particular perpendicular direction. So the particle-antiparticle should also have a similar kind of momentum. So therefore, the particle-antiparticle will move in this direction. So the combined linear momentum is also facing thiswards. And also the linear momentum is in this axis should be 0. And by imposing that, I can say that the angle at which the particle-antiparticle is created, let's suppose it is theta, is also equal. Why? Because the linear momentum in this perpendicular direction initially was 0. So the linear momentum in this perpendicular direction after the pair production should also be 0. So they should cancel each other out. Since they have same mass, they should be ejected at same angles to cancel out the linear momentum in this particular direction. The only linear momentum existing will be in this particular direction. So let's suppose the linear momentum of the electron is given by P and the linear momentum of the positron is given by P here. So the electron will have a linear momentum in this direction, which is given by P.
Oh, countdown to ads.
Are you? You look vaguely familiar.
Cos theta, yes. And the positron will also have a linear momentum in this particular direction, which is also given by P cos theta. Yes. So now we can look at the conservation laws of energy and momentum. First, let's look at the conservation law of energy. So if I write down the conservation law of energy, then I can say that the total amount of energy of the gamma photon, which is basically h nu, is basically equal to the total amount of energy of the electron and the positron, which is nothing but this particular equation. So the gamma photon leads to the creation of an electron-positron pair. So the relativistic mass of the electron-positron pair will come out of m naught c square. This is the first equation. This has to hold true for conservation of energy to hold true. Now let's look at the conservation of momentum. So the light photon has a momentum associated with it. Yes, the momentum of the light photon is nothing but its energy divided by the speed of light, which is E upon C. Yes, or this is equal to h nu upon C. So the momentum of the light photon is its energy upon C, or h nu upon C, and the momentum of the light photon in this direction is basically equal to the momentum of the electron and the positron, which is twice of 2p cos theta. Fine till now. What is p? P is nothing but the momentum of the particle here. So this is nothing but mass times its velocity. Now, as I already said, this mass is the relativistic mass. So we can write this as gamma m naught v. So this can be written as 2 gamma m naught v cos theta, or h nu is equal to 2 gamma m naught c v cos theta, or 2 gamma m naught c square v upon c cos theta. Now let's look at this particular term here. Here I have basically multiplied c in the denominator and the numerator. Why? You'll understand in a second. So v upon c, what is v upon c? V is the velocity of the electron and the positron. C is the velocity of light. So since the particles cannot move beyond the speed of light, so v upon c is always going to be less than 1. Also, cos theta can never have values greater than 1. Cos theta will also have values less than equal to 1. So in this particular term, which contains so many individual quantities, this quantity is less than 1. This quantity is also less than equal to 1. So I can say that h nu is basically less than 2 gamma m naught c square. Yeah, so 2 gamma m naught c square is being multiplied by two quantities whose values is always less than 1. So therefore, this equation I can say that this is less than 2 gamma m naught c square. So which is my second equation. As you can see, you can make a comparison between equation number 1 and equation number 2. In equation number 1, you have h nu is equal to 2 gamma m naught c square, and in equation number 2, you have h nu is less than 2 gamma m naught c square. This is a contradiction, no?
Good morning, team.
Oh, and it's a cliffhanger. It's a cliffhanger moment.
Conservation of energy tells us that these two quantities are equal, but conservation of momentum tells us that this quantity has to be less than this quantity. So this is a contradiction here. It cannot be true, because we know that both conservation of energy and conservation of momentum hold true in a given physical process. If these quantities are not conserved, then that kind of physical process is not possible. We end up getting a contradiction when we try to conserve both momentum and energy at the same time, which simply means that this kind of a process is not possible. This kind of a process does not conserve energy and momentum at the same time. So this kind of a process does not happen. The light photon does not become an electron and a positron because we cannot conserve momentum and energy simultaneously. The only way this kind of a process is possible is if there was some other physical object which could take some of the recoil of the initial light photon and make this equation equal. This can only happen if, let's suppose, there was some kind of a nucleus in its near vicinity. If there is a material medium in which this light was penetrating and there are lots of atoms, then this light photon, in the presence of some kind of an atomic nucleus, can lead to a creation of electron and a positron, because now the nucleus can experience some of the recoil of this particular process and balance this particular equation. As you can see here, this quantity is less than this. The only way I can prevent this kind of a contradiction is if in this term there was some other momentum, let's suppose P1 associated with it, and this P1 is nothing but the momentum transferred to some kind of a nearby atomic nucleus. So pair production can only happen in the presence of an external object like an atomic nucleus, which can experience some of the recoil in this particular process to conserve energy and momentum at the same time. So one important distinction between annihilation and pair creation is that annihilation can happen anywhere. If you look at the kinematics of this equation, energy and momentum is conserved in the pair annihilation case. But for pair production, you need an external atomic nucleus. So that is the answer to why a pair production cannot occur in empty space, because we cannot conserve energy and momentum at the same time. Now, I just want to make another point that this is also one of the most common ways in how extremely high energetic radiation interacts with matter. So you know about different kinds of phenomena that takes place when radiation interacts with matter. For example, for low energetic radiation can lead to photoelectric effect. Even lower energetic radiation can lead to some kind of a Rayleigh scattering. For medium energetic radiation can lead to Compton effect. For extremely high energetic radiation, which has sufficient energy, which is much greater than this particular value, when those kind of radiation interact with matter, then they lead to this kind of a pair production process. So that's it for today.
Okay, let me go to Carl real quick. Carl Rose. Carl, there you go.
Oh, that's
There you go.
great. So,
You know, in open discussion, you don't have to raise your hand, man. Just jump in.
oh, that's nice. Hey, Mike, I'm a huge fan. Every time you have something to say, I just want to shut up and listen. But no, it's so great because that's exactly the point of a Cooper's pair. So in a type 2 superconductor, you've got that really tiny channel, and you've got basically two negative electrons that are entangled because they're so close. And what happens is that in between them is a virtual particle, a Cooper's pair. And that is a virtual positively charged particle, a nucleus, a proton. It's a virtual proton. And that's what gets quantum locked. And to go back to what Todd was talking about with the gravity flyer, and it looked like it was like magnetically locked in place. That's what I think is happening. I think that it's like a type 2 superconductor, and it's quantum locked onto virtual particles. That's what it seems like, the analogy in my mind.
My reason for showing this is that my hypothesis is that there is no virtual pairs in the vacuum, and the vacuum energy isn't a result of virtual pairs, but as a result of proton flux, because the whole universe is in a proton flux. And if you're within the Oort shield of the sun, the proton flux is different than it is outside the Oort shield. And cosmic rays are essentially protons that are relativistic protons that hit the planet's atmosphere and mainly convert into muons, which are like, 209 times heavier than an electron.
So it's not a virtual particle. It's like a muon or something else that's taken on the guise of, like, it's filling in the void of the positive charge that needs to be there.
There is no empty space.
Yeah, I would go with that. Well, and then don't forget about neutrinos, right?
There's neutrinos too, but I mean, it's like if you take you can't have a free neutron. When you have a free neutron, it turns into a proton and an electron and a neutrino. Basically, protons are where the mass of matter comes from, not electrons. And in the semiconductor, they call protons holes, and they're mobile. But the thing is, there's a what I call anti-symmetric effect to mass. An electron is really light compared to a proton. It's like 1/1640th of the mass of a proton. So, and neutrons are just protons, essentially in a different form, a neutral proton. And so basically all the gravitational fields coming from protons. not electrons. But everybody's focused on electrons. So now the reason I wanted Ron to show his thing though is because what Ron is doing, he's using a chiral proton, essentially, a proton that has a certain special
Well, and that brings us back to Ron, who now has safety glasses, which terrifies me. But
Well, these materials are a tad nasty, and by being charged, these are the only material I had worse was a push-pull molecule called hold it, oh God, diamino. It was a push-pull molecule across the benzene ring. It was amino. Oh God, 2-methyl-4-nitroaniline. Okay, it's 2-methyl-4-nitroaniline on a benzene ring, a push-pull molecule, and it was not really that toxic, but the slightest bit. I tried dissolving some in alcohol because it was a polar molecule, and I was careful, and the slightest vapor of it caused a lot of eye irritation for about 2 or 3 days, and that was on the border of parts per million, and that was simply a push-pull molecule. This one is simply a chlorobenzene that's charged, and myself, I can tell. The thing is, I have an open end on it, which I do not like at all. But the best thing is to see the YouTube. I'll send it to Tim. This thing started. The whole thing is you can charge something by simply pouring it into a cavity. It's called triboelectric charging. There's a patent by me, 7340919. It has to do with the tribo charging of refrigerants, and it was popular. Oh God, about maybe 7, 8 years ago, when they were trying to increase the efficiency of air conditioning. But anyhow, it was very, very, very simple. And in there, I have a triboelectric chart. And I knew when I pour a dielectric into this cavity, I'd get a charge. I also knew by virtue of this material wanting to sublime through the initial charging, it would get more charge. And the thing is, this was never intended to be an electret cavity. It's metal. All my cavities are PVC. So I thought after it cooled down, I gave it like 4 hours to cool down. I put it on the scale, and then I flipped it over. The YouTube, which you saw, shows the difference. I was getting close to 1% weight change, face up versus face down, which is what Rhodes saw. What Rhodes saw with his transducer was 14% weight change, face up versus face down, on a chlorobenzene, chloronaphthalene electret. And so the only reason why I made the YouTube is because this was approaching 1%. I was hoping to break a 1% barrier. And then what happened is it started to decay. And I thought, it's going to take a while to make this another one of these. And so I went and recorded it on YouTube. And I figured I'll just put it up there and not get too involved. And then what I did is I figured, well, I have enough residual material to make one twice the size. And these are binary electrets. There's a 2-part component in the patent US 8901-890143. The binary electrets have a polar component, and they also have a non-polar component. The only trouble is, a lot of times your polar component is a chlorinated benzene, which is far heavier than your non-polar matrix. And the trouble with this is, I tell people these are very, very diode-like, because you're trapping electrons in interstitial lattice works. And so what happened is, this one was an ugly one because it did not want to form something homogeneous. And well, same with the other one. It didn't want to form anything homogeneous. And I had to keep stirring it to keep it from separating and bring it to a close temperature, and then allow it to solidify enough, and then let it settle down. And so normally, this one was a 2-3 ratio, a 2/3, 1/3. So I always try to get 2 experiments out of 1 run. So I made this one 50-50, and there was virtually no effect. The effect was minimal. So then I dropped it back to 2/3, and this one went over 1%. And I think by changing the ratios, and this is without DC charging. This is just, so anyways, that's where I am. So it's, if you want to mention more about it, Mike, you can. But also, what came out a few days earlier or weeks earlier, I started measuring I have my, by the way, this is my field meter, and these things, you cannot pick up much of a electrostatic charge on these. The charge, I have no idea what this is going to look like when it's under full power. It's possible that by being, when these triboelectrically charge, they're charged under a very clean electrostatic situation as compared when you make something from a voltage source. Because some people would make electrets from batteries. I don't want to have 500 batteries or a large group of batteries. I take my chances with AC powered power sources. But in terms of being a very clean power supply, you can't get a more natural power supply than triboelectric charging. Or I think I could go Van de Graaff, because my friend Boyd Bushman, in his electret patents, he went Van de Graaff. So I may have to use Van de Graaff to get something clean. It's just that this all happened within the past. This one is like 10 days old. The bigger one is maybe 3 days old. And this one is more stable for various reasons. But when I went to 50-50, there was nothing here. I cut back to this, and by virtue of size and I didn't want to make a YouTube until I beat Podkletnov. That was my goal. And it's just when you see things deteriorating, you figure, well, it might be a while till you get back there, or you may never get back there. But what I want to mention, there is when I was monitoring my other electrets, I realized some of my electrets were monopolar. There was no, and then I started researching monopolar electrets. Back in, it's in the YouTube. If you type in YouTube monopolar electret in my name, you'll pull up the monopolar electret. The Sony Corporation, they had a set of earphones and speakers. Sony back in 1976 had the Unibrand. It was a unipolar electret speakers and headphones.
Cool.
And then
yeah, they made 6 different variations of that model, and all of them are reported to be incredibly popular. They're quite expensive now and hard to find, and I'm noticing now that a lot of material scientists are buying them just to pull the monopolar electrets out of them.
Yeah. Well, anyhow, I contacted the professor. The professor's name is Coeth, C-O-E-T-H. It's a hard name to memorize. He's at the University of Maryland, and he was talking about the intrinsic instability he's making in my US, whatever hell number that is, doesn't matter. I mentioned about radioelectrets, and he made a, he used the word monopole or monopolar. And anyhow, this goes back maybe it's 5 years. I found the paper and his name after this stuff has been on Google all along, but I never envisioned in the YouTube that I made. I said, well, I never envisioned a monopolar electret. I thought it's nonsense. It wasn't until I started taking readings and I started looking at the way things were constructed. I'm saying, well, I have a monopolar electret here, and I'm going to search it out of curiosity, and because you usually get monopole magnets, never found, this and that. And I mentioned it, and the YouTube runs, I think, 29 minutes. The one on the electret shield with the tin cans, that runs 13 minutes.
Yeah.
If you have any trouble finding,
Got that one queued up, Ron, and what I'm doing is I'm not showing the whole thing. I'm just cutting to the chase, basically.
oh yeah, fine, yeah, I have no problem. I mean, I'm I'm gonna finish up here. So if you wanna, like I said, when I saw that Sony made the monopolar electret back in, the only thing is I never really investigated it because I thought I had a discovery of monopolar electret. Then I realized Sony had it. And then Professor Coeth, C-O-E-T-H, University of Maryland, he made them. And then I started looking around, and the concept of homopolar, unipolar, monopolar electret, it's not new. It's just people don't know about it. And so there's so much crap to what I'm doing. And so in terms of, I'm giving myself a rest, mainly due to exposure and stuff. And I'll probably write different ratios to work out. And I might go into matrix work for a while. But so Rose was right. Rose was right. Because I've seen this in what Tim will like, also the other David who was on earlier with the Paris. When this is bizarre with this electret here, I found out a lot of times I let my scale warm up for minimal half of an hour, even though it's electronic and digital. There's something that I saw called weight sag, that when you take some readings and you let it sit for a while, the readings will not be stable. And so I get things warm. I run my test samples on it, make sure the my test, it's a piece of ceramic and it's not affected by humidity. And make sure I get like 5 readings to the point on that ceramic, and then I'll weigh it. And what I do is with my inversion, I started flipping and flipping and flipping. And what happens is, I've noticed this from even years ago on smaller effects, that when you start flipping them, after so many effects, you start to lose and I think it has to do with the internal motions of what goes on inside the material. Because when Tim was saying about persistence of the effects with Lifter, and Paris said the same thing when you shut the power off, but there's something.
And PNN says the same thing, and Eric Dollard said the same thing, and then it goes back through history, and it's been said again and again and again and again, all the way back to the 1890s.
Yeah, because I'm not sure if it's the benzene rings. With benzene rings, you have ring currents, and the ring currents could be somewhat I won't use the word gyroscopic, but it's probably the best representation of it. And you start messing with it, and because I had a situation just recently, I thought something went wrong with my scale, and I said, I know what's going on here, because the first thing you want to do is to say, the effect went away, it's not real, do something else. And I let it sit for a while, and I knew I exceeded its happiness point. And then it came back again, but it was just weird. I go, because my worriment is you make something, you get an effect, and then I've had this happen before. You shoot yourself. It's simply easier to get reincarnated. That's it. So Mike, if you want to describe, you want to do the short of the clips.
Yeah, I'm going to go ahead and share it.
Before that, let me interject one quick point. Ron, please, for the love of God, get a flow hood. I don't care if you have to go to Home Depot and buy a pan and a fan, but set up a flow hood, man.
No. Well,
please.
Rest assured, I am only trouble. Never mind. But
okay, can you guys see that?
I want to save your mind because we need it.
Is that coming through? Can you see him? Hello.
Are you talking?
Yeah, we can see him.
500 grams. And when he took it from one side of the scale to the other side of the scale, he accidentally flipped it over. And what happened is the steel plate was on the top, the dielectric was on the bottom, and the electret dielectric,
okay, here we go.
0 gram weight here. This is open air. And I'm going to try to get this on here. This will probably be a short YouTube. Already I'm into 5 minutes on it. So I was hoping to do a sample of 10. This is very repeatable. I've gotten as high as 0.04 of a gram differential. My goal was to get to 0.05 of the gram differential. This is sliding back towards the 2 to 3 gram range. And I want to see what I can film here. And this will be updated and taken down for better everyone. So I'm gonna have to go around back here so I can watch the scale. In terms of the calibration of the scale, this is what I use as my calibration. It's a ceramic coaster. And I'm gonna put this on the scale. It's gonna weigh about 100 grams. I'm gonna tear it to 0. Then I'm gonna start flipping and weighing this electret. And you're gonna see, hopefully you'll see differential in the weights of it. I have no idea, but this has been running good for 10 days. And now it's getting to the end of its life. And like I said, this will be upgraded. And so I'm gonna put this on here, go around back so I can see the numbers, what is going on here. Also, I got count to 0. I'll be hitting 0 a lot and just seeing where this goes. And hopefully it will tend to show something. Okay, let's see here. I'm going to go around back because breathing on the scale will change the weight significantly. What I'm talking about per hundredths of a gram, but we'll see. Like I said, this was getting close to demonstrating 100% gravity modification without any power, nothing, just pure internal electrostatics on benzene ring material. And I found it exciting. Whether anybody else does, I'm not quite sure. So I'm going to go around back here. Let's see what I can get here. Oh, I got to let's put this. Let's see what's. Hopefully this is. Hopefully this will stay here. Okay, so far so good. Okay. I'm going to hit 0 this again. I'm going to start weighing this. I might take several samples. I'd like to run samples of 10 for t-tables for those who want to do the statistics on the probabilities of what the success is. So I'm going to go here. I won't see the screen anymore, and hopefully it'll. Okay, this weighs 0. But what I'm going to do is weigh the bottom. This is the bottom. The bottom should be heavier. And when I flip it over, the top should be lighter. Not by much. Okay, this is 8791. Okay, let's say should go back to 8. This is I'm just checking. I'm just doing repeat checks on this. It might take a little while to go back to 81, 8791. I don't want to speed up the scale. Sometimes you have to. I may have to. This should take a. I'm going to start over again. See if I get 81, which is more real. Okay, it seems to be happy at 8790. Just. And now I'm going to flip this over and I'm going to see if it weighs less than 87. Will this weigh lower than 8790? I don't want to rush the scale. Okay, this is about what it runs. It runs about, okay, this is a 2 gram differential.
0.2 of a gram.
Yeah, I'll zero it again. Okay, this is 8791. It's on the margin between 8790. It's coming back to 90. Okay, I'm going to take this off, 0 it, and with this on top, I'm going to see if this weighs less than 90. It's weighing about 2 grams differential. I'm going to let it sit for a while. Okay, I'm going to weigh on the bottom again. It seems to want to weigh 8790. Let's see if it weighs 8790 again. Okay, let it sit there so I don't interfere with it. Okay, let's see if it weighs less than 8790. Does it weigh less than 8790? Okay, this is what it's running at. We'll do it again. See if we get, okay, ticked off one. Got 8790, which looks like a good weight. Going to turn this over, see if it's less than 8790. Okay, that should drop down to 88. I've been getting differentials of 3, some as high as 4. And that's about the end of the demonstration. No sense doing more samples than that. And let me see, I'm going to turn this off here. I'm going to turn this off.
So that's pretty cool, Ron. It's what's important. It's the amount isn't as important as the proof of concept in my mind. It shows the proof of concept.
Pardon?
I said the amount of weight change isn't really relevant to the proof of concept. The concept, the conceptual basis of it is you can show conceptually it works. That and if you can do 0.2 of a gram, that doesn't. There's no reason that it shouldn't be able to adjust cause significant weight loss with the proper. It should be able to be essentially weightless with the right configuration. Correct.
It's been years. The reason why I get up every day, I've seen similar, but the thing is, in terms of getting an effect that's persistent, these electrets, the main thing is people should go through, take a look at the not homopolar, monopole electret. There's some insight there. This is the main thing is also what's even larger. When I have a sealed cavity, I can lose 25%, and I know this cavity is sealed. On a sealed cavity, I can lose 25%, and I know there's a perfectly good seal in that cavity. And I have no explanation. I have no explanation why a sealed that.
When you say sealed, do you mean it's
in the earlier part? In the earlier part, when I had that flip over electret.
Okay, yeah.
That is sealed, like you would not believe. Okay, and I wouldn't say 20. I know at least 20% over. It might take a while, but all the lens, the cover on that lens, is from a CD, music disc, a CD-ROM, whatever.
Right.
And if there's any sublimation, that lens will fog. And so I know it's not sublimation. I know it's not getting out through the edges. I have no explanation. I don't really talk about it.
Inside the cavity besides the electret?
Well, it's in the early part.
Is it a vacuum in the cavity, or is it just
Well, if you wait a second, I'll grab it. Hang on. Hold on.
Okay, guys, sorry. Let me cut into Ron really quick. And I should apologize because I know Ron was in the middle of something, but let me see. Oops. Okay.
There he is.
Oh, Ron, let me wrong one. Oops.
That's good. Hey, more.
Nope, that's okay. No, sorry. Mark asked me to go to Brenda's camera. So Mark wants to do some more interviews. Some more presenters showed up.
Okay, well, that's all. So it's for Mike. It's all. This is what the seal looks like.
Gotcha. Yeah,
Okay.
I was just curious if it was evacuated, if it was an evacuated chamber or if it had.
Well, it's epoxy, 5-minute epoxy or longer. I like better epoxy, but this is, it's very good. It's perfect as you can get. So,
Okay,
okay,
thank
bye,
you.
gang.
Oh, okay, okay. Sorry about that. There,